Snell's law is a simple mathematical way of describing refraction. Refraction is an observed property of light of bending in direction when traveling between two mediums. This is commonly observed as the broken image effect of objects placed in liquids, but also has important uses in corrective eyewear and, of course, astronomy. The underlying cause for refraction is the change in speed of light as it interacts with the particles of the medium that it travels through. Much like if you have rows of a marching band traveling between pavement, which is easy to walk through, and mud, where they will slow down, the rows are going to change direction. For light, these rows are equivalent to the wavefronts. Snell's law gives the exact mathematical relationship of the geometry. The ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of the phase velocity of light between the incident and refracting media. The angles are measured with respect to the normal to the surface at the point where the incident ray strikes the interface. While we can express the law in terms of the phase velocities, these velocities are not measured directly. Hence, we express the law in terms of a different constant that is based on the properties of the material, known as the index of refraction, denoted by lowercase n. Note that in the formulation of the law, the direction of light is not specified, hence it is arbitrary, which we call the incident or refracted ray. From here onward, we will just index them by number. To simulate Snell's law, we are going to borrow the simulation from the University of Nebraska-Lincoln astronomy website. Snell's law is written in mathematical form at the top. The thick, dark line is going to be the interface between two mediums, 1 and 2. You have a laser pointer and a light beam, red in color, that you can drag or rotate. The normal to the surface is automatically drawn in for you, and the angles are calculated for you. When the indices of refraction are the same, then there will be no change in the angle between the incident and refracted rays, no matter what the medium is. Only a change in medium will induce bending. Also, bending is only relevant if the angle is non-zero. If the index of refraction of the second medium is greater than that of the first medium, then the light is going to bend towards the normal. The greater the difference in the indices of refraction, the greater this effect is. The incident material does not have to be the one with the lower index of refraction. If the index of refraction of the incident material is the one that is greater than for the refracted rays, then the angle of refraction will be greater than the incident angle. The light will bend away from the normal. In fact, this has important implications for fiber optics. When the index of refraction of the incident medium is so great, then at greater angles of incidence, there won't be a refracted ray, rather there will be what is referred to as internal reflection. Internal reflection is what allows the transmission of light beams and signals through curved optical cables.